This video is an introduction to series and convergence. This unit is only found in AP Calculus BC, and it is not part of the AP Calculus AB curriculum. Let's lay down some vocabulary as a foundation to build on. A sequence is an ordered list of things. I'm keeping it very general. For example, this list is a sequence. The fact that it is ordered means that the order matters. If I changed the order, it would be a different sequence. A series is the sum of the elements of a sequence. For example, if I take the sequence from example 1 and add up all the elements, now it's a series. A series has two types, infinite and finite. An infinite series has an infinite number of terms. For example, 2 plus 4 plus 6 plus 8 and so on is an infinite series. On the other hand, a finite series has a finite number of terms. For example, 5 plus 4 plus 3 plus 2 plus 1 is a finite series. It has a first term and a last term. It doesn't have to have any special order to be a finite series. In fact, the example I gave right at the beginning is another finite series. Let's talk about sigma notation. This big letter that looks like an E is the capital Greek letter sigma. The n equals 4 at the bottom means that 4 is the starting index, and the 7 at the top means that 7 is the ending index. In math, the sigma itself means sum, so we're going to be adding something. This expression represents the sum of all terms an, starting with a4 and ending with a7. An represents some type of rule. So, for example, on this problem, n plus 2 to the n power would be the an. So this expression represents the sum of all terms of the form n plus 2 to the n power, starting with 0 and ending with 3. So even though we see a 3 here, it's actually 4 terms. This is one that we are actually able to evaluate. This series equals 145. You can write an infinite series in sigma notation by putting an infinity on the top. This series is the sum of all terms an stretching out forever. Partial sum sk is the sum of all terms of a series up to ak. For example, for the series above, S3 is the sum of all terms up to A3. Notice that even though this is called S3, it actually has 4 terms, including A0. A series can either converge or diverge. It converges if the limit of partial sum sk as k approaches infinity exists. And it diverges if the limit does not exist. Put another way, a series converges if the infinite series equals a number, and it diverges if the infinite series does not equal a number. I want to briefly mention how this relates to something you already know. Back in Unit 6, we learned about improper integrals, like the integral from 0 to infinity of f of x dx. It was improper because of the infinity. We learned that an improper integral will either converge to a number or diverge. Given antiderivative capital F of x, we learned that the improper integral would equal the limit of the antiderivative as x approaches infinity minus the limit as x approaches 0. We learned that if both limits exist, the integral converges, and if either limit does not exist, the integral diverges. In this unit, we will not use our graphing calculator very often, but for this exercise, I want you to use the calculator to help you get a feel for whether a partial sum converges or diverges. We are going to use the first several partial sums to predict whether each series converges or diverges. Then we will try to predict the sum of each convergent series. In other words, if the series converges, we are going to try to predict what it converges to. This first series is going 3 over 10 to the 1 plus 3 over 10 to the 2 plus 3 over 10 to the 3 plus 3 over 10 to the 4, etc. So partial sum S1 would be 3 over 10 to the 1, which would be 0.3. Partial sum S2 is the previous partial sum plus term 2, but this is 3 divided by 100, or 0.03. Mentally, we can see that 0.3 plus 0.03 equals 0.33. Let's do one more by hand, then we'll switch over to the calculator. Partial sum S3 will be the previous partial sum plus term 3, but this is 3 thousandths, in other words, 0.003. And even without a calculator, we can see that 0.33 plus 0.003 is 0.333. Here's how you do successive partial sums on a calculator. Remember, we are doing 3 over 10 to the n, so let's go through the motions and start off with 3 over 10 to the 1. So obviously we get 0.3. Now we want to do the next partial sum, which will be the previous partial sum plus the term 2. So I'm just going to hit plus, because that automatically includes what came before, and we will do plus 3 over 10 to the 2. So this is the next partial sum. It's not the next term, it's the next partial sum. If I want partial sum S3, I want to include everything that has come before plus term 3. If I simply hit plus, that includes everything that has come before, so that's the 0.33 plus term 3, so plus 3 over 10 to the third. So this is what we did by hand. Let's just do a few more, even though this pattern is so clear that I'm sure you can see where this is headed. If I do plus 3 over 10 to the 4, we get this, and if I do plus 3 over 10 to the 5, we get this. So if I kept going in this way, all the way to infinity, we would get 0.33333 repeating. So what's happening? We will say that the series appears to converge to 1/3, because 0.3 repeating is 1/3. We will spend the rest of this unit learning how to prove definitively whether or not a series converges or diverges. But we don't know those proofs yet, so this is the best we can do. Notice that the next example starts at 0, and it's going 0 over 2 to the 0, plus 1 over 2 to the 1, plus 2 over 2 to the 2, etc. Let's go to the calculator. Let's go through the motion starting with 0 over 2 to the 0. So we start with this. Now we're doing partial sums. We want to always include what came before, so I'm going to immediately hit plus. And so now it will be 1 over 2 to the 1 plus 2 over 2 to the 2. Okay? And I want you to watch what's happening to these numbers and see if it seems to be approaching a certain value, or if you think it will keep going on and on forever without leveling off. So let's hit plus 3 over 2 to the 3 plus 4 over 2 to the 4 plus 5 over 2 to the 5 plus 6 over 2 to the 6. All right, any guesses yet? Let's do a few more. Plus 7 over 2 to the 7. One more. plus 8 over 2 to the 8. What seems to be happening? Well, we are getting closer and closer to 2, but I bet no matter how far we went, we would never go past 2. We say that this series appears to converge to 2. I encourage you to pause the video and play around with these two examples on your own. See if you can make a prediction. This series is a little strange because the rule is just n. That means the sum will be 0 plus 1 plus 2 plus 3 and so on. This is so simple that we're not going to bother with the calculator. Partial sum S0 is just 0. Then partial sum S1 is 0 plus 1, which is 1. And partial sum S2 is 0 plus 1 plus 2, which is 3. And then partial sum S3 is 0 plus 1 plus 2 plus 3, which is 6. Obviously, this will just keep getting bigger and bigger and bigger without bound. Without a proof, we can only say that the series appears to diverge. For this last example, the rule is 1 over n. So the series is 1 over 1 plus 1 over 2 plus 1 over 3 and so on. Let's take a look at the partial sums in the calculator. S1 is a single term 1 over 1. S2 will be this plus the next term 1 over 2. S3 will be this plus the next term 1 over 3. And so on, plus 1 over 4, plus 1 over 5. Alright, so let's make a guess. Maybe this will level off at 3, and it won't go past 3. We've already gone past 1 and we've gone past 2, so maybe it won't go past 3. Let's see. Plus 1 over 6. Plus 1 over 7, plus 1 over 8, plus 1 over 9. Wow, getting really close to 3. Maybe it won't go past it. Maybe that'll be the limit. Plus 1 over 10, plus 1 over 11. Oh, we blasted past 3. So here's the thing, guys. This is just going to keep getting bigger and bigger forever. If I said, maybe the limit's going to be 4. If I kept adding another term and another term and another term, eventually I would pass 4. I would pass 5. I would pass 10. It never stops. This series appears to diverge, and this is the strongest statement that we can make until we learn how to prove it. To prove convergence or divergence, we use tools called tests. And I'm going to teach you your first test right now. The first test is called the nth term test. And it is first not only because it's the first test I'm teaching you, but because it's the test I want you to use before you do anything else. To begin the nth term test, you consider the limit as n approaches infinity of an. Notice that we are talking about what happens to the value of individual terms as n approaches infinity, not partial sums. There are only two possibilities. Either the limit equals 0 or it doesn't. Here's the part I need you to memorize. If the value of the rule approaches 0, it gives you no information. You just have to keep going. Maybe the series converges, maybe it diverges. You know nothing. On the other hand, if the value of the rule does not approach 0, then the series diverges. Again, if the limit does not equal 0, we can be 100% sure that the series diverges. Danger, caution. This is a common mistake that students make, so I want to emphasize what the nth term test can and cannot do. The nth term test can prove a series diverges. However, the nth term test cannot prove a series converges. Determine whether the nth term test tells us the series definitely diverges, or if the nth term test gives no information. Remember, this rule right here is an, and for the nth term test, we need to find the limit as n approaches infinity of an. Notice that the numerator is a constant. As n approaches infinity, the denominator will get bigger and bigger and bigger. Therefore, the overall value of the expression gets smaller and smaller and smaller, and the limit is 0. The value of the rule is approaching 0. But the nth term test says that if the limit equals 0, it gives us no information. We just have to keep going. So that's it for the first example. Let's look at the next one. As we consider the limit of this expression as n approaches infinity, we focus on what matters most. In the numerator, we have 3n. In the denominator, the 4n is what matters most. So think of this as 3n over 4n. That reduces down to 3/4. So guess what? That's the limit. But the significance of this is it does not equal 0. And according to the nth term test, if the limit does not equal 0, the series definitely diverges. This string of information is a little proof, proving the series diverges. I want you to think of this proof as having 5 parts to it. And to get full credit on your test, your proof needs to have all 5 parts. Let me list the 5 parts for you off to the side. This divergence proof has 5 parts to it: setup, result, significance, conclusion, and test. Let me show you what I mean. For the nth term test, we always start by considering the limit of the rule as n approaches infinity. So that part is the setup. Then we found the limit, and it turned out to be 3/4. So that's the result. But what's the significance of this number? What aspect of 3/4 tells us the answer? Is it the fact that this number is positive? Is that what's important? Is it the fact that this is less than 1? The significance of 3/4 is that it is not equal to 0. That's the aspect of 3/4 that tells us the answer. And that's the third part that must be included. This leads us to the conclusion that the series diverges. Wait a minute. I only see 4 parts here. I told you that a proof needs 5 parts. That means this proof is incomplete. You have to say the series diverges by the nth term test. The proof is not complete without the naming of the test. This is a key part of your justification. It looks like we're going to be finding a lot of limits in this unit, so this is probably a good time to review some of the most common strategies that we've learned. FEPL is an acronym that stands for factorial, exponential, polynomial, and logarithmic. It ranks the various types of expressions from faster growing to slower growing as x approaches infinity. For example, consider the limit as x approaches infinity of natural log x over 3 to the x. This is a logarithmic expression over an exponential expression. FEPL reminds us that the denominator is growing faster than the numerator as x approaches infinity. So, since the denominator is getting bigger and bigger compared to the numerator, the overall value of the fraction is getting smaller and smaller and smaller. More specifically, it's getting closer and closer to 0. So that's the limit. WMM is another acronym that stands for what matters most as x approaches infinity. For example, consider the limit of this expression as x approaches infinity. In the numerator, the 3x squared matters most. It has the highest degree and it's going to be growing a lot faster than the 5x. In the denominator, the 2x squared matters most for the same reason. The limit of the original expression is the same as the limit of 3x squared over 2x squared as x approaches infinity. But the x squared cancels out and you get 3 over 2. So that's the limit. Then there's good old L'Hopital's rule, which says that if the limit as x approaches c approaches 0 over 0 or infinity over infinity, then the limit as x approaches c of f over g is the same as the limit of f prime over g prime. For example, consider the limit as x approaches 0 of sine x over x. Direct substitution gives us 0 over 0. So it satisfies L'Hopital's rule. Therefore, we can take the derivative of the numerator and the denominator without changing the limit. The derivative of sine is cosine, and the derivative of x is 1. We can find this limit by direct substitution, because the cosine of 0 is 1. Determine whether the nth term test tells us the series definitely diverges, or if the nth term test gives no information. For the nth term test, we start by considering the limit of the rule as n approaches infinity. We can find this limit using a combination of Feppel and what matters most. In the numerator, 8n squared matters most, so I'm going to ignore the 4n. Of course, in the denominator, all we have is 2 to the nth power. Focusing on these two terms, we will now use Feppel. So in the numerator, we have a polynomial expression, while in the denominator, we have an exponential expression. Exponential grows faster than polynomial, so that means the denominator is getting bigger and bigger compared to the numerator. Therefore, the overall value of the fraction is getting closer and closer to 0. But according to the nth term test, the fact that the limit equals 0 gives no information. For the second example, we again begin by considering the limit of this expression as n approaches infinity. We will again use a combination of Feppel and what matters most. In the denominator, the n factorial matters more than the 5n. And I'm sort of using Feppel here in the denominator because the f in Feppel stands for factorial, which grows faster than the polynomial 5n. So that's why n factorial matters most. In the numerator, we just have the exponential expression 3n. So these are the only two terms I'm going to consider. Now between those two, as I mentioned, we have an exponential versus a factorial. But according to Feppel, factorial grows faster than exponential. So just like in the previous example, the denominator is getting bigger and bigger compared to the numerator. So the overall value of the fraction is getting closer and closer to 0. And according to the nth term test, this gives us no information. Let's do two more examples. What happens to the limit of this rule as n approaches infinity? This will be Feppel again. In the numerator, we have a logarithmic expression, and in the denominator, we have a tiny polynomial. According to Feppel, polynomials grow faster than logarithms as n approaches infinity. So once again, the denominator is going to be getting bigger and bigger compared to the numerator. So the overall value of the fraction is getting closer and closer to 0. So again, according to the nth term test, this gives no information. The next example is the same problem, but flipped upside down. So this time we have a polynomial over a logarithm. And according to Feppel, polynomials grow faster than logarithms as n approaches infinity. So since the numerator is getting bigger and bigger compared to the denominator, the overall value of the fraction just keeps growing bigger and bigger and bigger forever. So the limit approaches infinity, or I like to say the limit does not exist. And based on this, we can conclude that the series definitely diverges. But wait a minute, if you put this answer on your test, you're only going to get half credit, if that. What are we missing? What's wrong with this answer? This proof of divergence is supposed to have 5 parts to it: setup, result, significance, conclusion, and test. Can you tell which parts we're missing? The limit is the setup, so we have that. We mentioned that the limit does not exist, so that's the result. However, what aspect of this tells us that the series diverges? The significance is that the limit does not equal 0. So that's what we were missing. Well, that's one thing we were missing. We can check it off now. We stated that the series diverges, so that was the conclusion. But the proof is not complete without mentioning what test we used. We must say the series diverges by the nth term test. Now we have all 5 parts to our proof, and now we get full credit on the test.